Okay, in this tutorial, which hopefully will be very brief, I just want to go through the process of setting up a simulation with a 2N3904 bipolar transistor and doing a logarithmic sweep. So we're going to start out by making a new schematic, and we're going to drop down an NPN bipolar transistor. And we're going to want to sweep the current. So we'll flip this around. And let's put it there. And let's diode connect this transistor, which means we connect the base terminal to the collector. And we're going to be connecting the input current source to that base and collector terminal. And now we're just going to tie these two nodes to ground. So that's the emitter of the transistor. And let's call this IN. And we can give it a nominal value of, let's say, I don't know, 100 microamps. And we can label this node VN, let's say. And we're going to need to include engr2420.sub as usual. And now there's a couple things we need to do. One is we need to take this transistor and we need to say that we want to make this transistor behave like A2N3904. And the way that we do that is we right-click on it and put in 2N3904. And maybe this wants to be a capital N. And so that will basically say I want to use the model parameters that are tuned up to match the behavior of one of these discrete transistors that we would typically use in this particular lab that we're working on. Okay, next thing is that we're going to be sweeping the current over quite a range here. The lab handout suggests I think 1 nanoamp up to 10 milliamps. And one of the things that Spice has built into it is some amount of numerical slop that's allowed in the satisfaction of Kirchhoff's current law at each node as it's trying to find the value of DC voltages in the circuit that will be consistent with the device's IV characteristics and Kirchhoff's laws. Having the sum of the currents equal to 0 is too stringent a numerical condition, and so there is a little bit of slop allowed, and that slop is a parameter called ABSTOL, A-B-S-T-O-L, absolute tolerance. It has units of current, and it's something that you can find in the tools, the control panel. And if you look here on the tab that comes up, here is the absolute current tolerance. So that is ABSTOL, and you can see that it's set here to 1 times 10 to the minus 9, which is 1 nanoamp. So for simulating circuits that have milliamps or even microamps running through them, a nanoamp is a perfectly reasonable value to set for this amount of slop that's allowed. However, if we're actually at some points going to be working with currents that are on the order of that slop, that means that our simulation results could very easily be quite inaccurate. And so for this particular lab, since we're dealing with the currents that are on the order of a nanoamp, we're going to turn this down to 1 picoamp, 1 times 10 to the minus 12. And that's something that requires some judgment, and for some of the circuits that we'll be dealing with simulating in this particular course, that will prove to be a good thing to do to get accurate simulations. Okay, so with those two things done, now we can basically run our simulation. We're going to be interested in a DC sweep, as we have been. We're going to be sweeping, in this case, the input current source. And now we have to select the type of sweep. And so to do a logarithmic sweep, which is equally spaced points on a logarithmic scale, we can choose either octave or decade. Okay, so what we specify is the number of points per octave or the number of points per decade in each of these two cases. Now, an octave is a factor of 2. For some reason, I don't know actually why octave is the word that we use for a factor of 2. Since oct is 8, it may have something to do with the number of tones in one octave in a musical scale or something like that. Because two notes that are the same, that are one octave apart on a piano, are a factor of 2 in actual frequency apart from each other, and maybe there are 8 full steps or something like that in one octave, or I don't even know. But an octave is a factor of 2, and a decade is a factor of 10. And so we're going to choose decade, and we have a starting value and a stopping value. And I'm going to put in here for the starting value 1 E minus 9 for 1 nanoamp. And for stopping value, I'm going to put in 10 E minus 3. Now that's, let's see, 1 nanoamp, 10 nanoamps, 100 nanoamps, 1 microamp, 10 microamps, 100 microamps, 1 milliamp. So that's going to be 7 decades plus 1 point on the end. Okay, so if I want to get something on the order of like 100-ish points, I have to choose the number of points per decade to get that. So I'm going to pick, I don't know, maybe 15 points per decade. That seems like a reasonable number of points. And I'm going to do that. And you can see down here on the horizontal axis, I have a log scale, which you can tell by the fact that these current values are labeled here in increasing orders of magnitude, one factor of 10 apart here. And you can tell also because the tick marks get bunched up near the end of the decade. So let's zoom in. Here, and let's just click on the input. And so you can see that at 1 nanoamp, our voltage across the diode connected transistor starts out at about 0.3 volts, and at the other end, at 10 milliamps, it goes up to about 720 millivolts. And so it's changing by only maybe 450 millivolts or maybe 500 millivolts over that 1, 2, 3, 4, 5, 6, 7 decade range of current. And it's a very nice straight line. So we can right-click on the plot, view data points. So you can see there are data points. So that seems like a reasonable number of data points. They're not so close together that they overlap, and yet there are quite a few of them. So that's how we would do a logarithmic sweep. That's one of the things you're going to have to be doing for experiment 1 in lab 2 in simulation, and just wanted to do a quick tutorial to show you how to set that up. The export is the same kind of deal. You click on the plot window, you go up here, you export data as text. Here we're saving, might as well try to load it into MATLAB. Diode, this is a voltage current characteristic. Probably don't need to save this. Open up my documents. Take diode IV, stick it in my MATLAB folder. Run MATLAB. there it is, IN VN, 106 points. Pretty much just what I had hoped in terms of about 100 points. And if we do semi log y, in this case, well, I'll do semi log x. IN VN. There we go. So there you have it. Hopefully that makes sense, and we'll see you in the next one.